can talk about second derivatives, second order derivatives in multivariable calculus, just like in one variable. So suppose you have f of x comma y as, say, x cubed plus 5x squared y. And let's say vector u is following vector 3 over 5 comma 4 over 5. Now I don't know the angle of this direction, but that's definitely a unit vector, right? Okay, and here's what I want to ask. Find directional derivative of f with respect to u, and that function's directional derivative. Now let's think about what this means. First, if you take the directional derivative of f, that's still a function of x and y, right? Because directional derivatives, I mean, if you're given this direction, like that, let's say this is the vector u. Depending on where your x comma y is, the rate of change here, there, all in this direction will be different, right? So it really depends on x and y. So this, if you compute this, this will be a function of x and y. And therefore, that function can be still differentiated by u. Now, if you didn't understand what I just said, you'll understand it as we compute this. Okay? So let's try to compute this. First, directional derivative of f. Let's start from the inside. We first compute this, and then whatever we get with it, and then we compute it again. That's what we're going to do. Okay? So let's just first compute directional derivative of f with respect to u. What is that? That's gradient of f dotted with u. That's the formula, right? Now let's compute the gradient. What's the gradient? It's a vector made up of all the partial derivatives, right? So let's first differentiate by x. What do we get? 3x squared plus 10xy. Okay. Now, what about the next one? If you differentiate this by y, you get 5x squared, right? That's what it is. Okay. And then you do a dot product with 3 over 5 comma 4 over 5. So we compute the dot product. It's a component-wise multiplication, so x components multiply together, and the y components multiply together, and then you add the results. Okay, that's what dot product is. So 3x squared times 3 over 5, that's 9 over 5 x squared. 10xy times 3 over 5, well 10 divided by 5 is 2, so 2 times 3 is 6, so you have 6xy. And then 5x squared times 4 over 5, that's just 4x squared. So that's the directional derivative at any point x comma y in the direction of this vector, unit vector u. So that's what we have. Okay, so what is this? This is a function of x and y, right? Therefore, we can differentiate again. That's what it's asking me. I want to differentiate this twice in the direction u. So let's do that. Let's differentiate this again. So this would be taking the directional derivative of duf, which is this thing, 9 over 5 x squared plus 6xy plus 4x squared. Okay. That's what the question is asking us to calculate. What is that? That's the gradient of this entire thing, right? So that's 18 over 5x and 6y, 6y, 8x, comma, this is what you get if you differentiate by x, the entire thing. Okay? Don't put commas here. You're going to ruin everything if you do that. So this is partial with respect to x. And then what's the partial with respect to y? 6x. So that's the gradient of this function. Now what do you do?
Dot of u.
Dot of u, which is 3 over 5, 4 over 5. Therefore, that's 54 over 5x plus 18 over 5y, 24 over 5x. That's what I get if I multiply this to the first one. Right? It's a component-wise multiplication that you add. These two are y coordinates, y components, so we multiply them. 24 over 5x. And then if you want, you can combine all of them together. I see these are like terms, right? That's 24 plus 24 is 48. 48 plus 54 is 102. Okay. So that's what this calculation gives us. That's the second derivative. Now, what would be the meaning of this calculation? What would be the meaning of this? Do you have any idea? It's a second derivative in the direction u, so what would it measure?
Acceleration.
Huh?
Acceleration.
Okay, so you can think of it as like now that's hard to say because for a second derivative to be acceleration, you should be differentiating by time. That would mean that this x and y are both time dimensions. I know there are some really strange physical theories where they have time as 2 time dimensions rather than 1. So I guess it makes sense in that case, but I think the more fitting description is just thinking about the geometry of the function. So what has the second derivative have anything to do with the shape of a function? Huh?
If it's increasing.
No, the first derivative tells you if it's increasing or decreasing, right? Yes. Second derivative tells us the concavity of the function, right? So what this is doing is, for example, in this region where x and y are both positive, this will be positive. So this tells us that in this region at least, the graph of the function is concave in this u's direction. Now, we learned that there are things like saddles where it's concave the other way. If this is positive, it's concave up. If it's negative, it'll be concave down. So it's possible that on this way it's concave down, but at least we know that it's concave up this way. So we can get some geometrical information by even taking 2 derivatives with respect to one direction.